Hello, and welcome to the third video lecture from section 2.1, talking about first-order linear equations. So in this video, I'm going to do a quick little trick for how you can start the problems a little bit quicker, and then we'll go through two examples of how to solve these first-order linear equations, showing you how the solution sort of comes together, and you get your final answer out of that. Let's go ahead and jump on in. So first of all, a little trick for doing these equations. Basically a trick for finding integrating factors. All right, so as we saw in the last video, the equation for finding an integrating factor is of this form. d mu dt equals p of t mu of t. Now, how do we solve this? We can solve this, since it's a separable equation, we can just solve it directly. I get 1 over mu d mu dt equals p of t. And then in a separable equation, I can integrate both sides. So I get a log of mu equals an integral of p of s ds plus a constant. So if capital A is an antiderivative for p of t, this becomes log of mu equals a of t plus c. So then mu is just a constant times e to the a of t. And that's always the case. So the trick is I can just find an antiderivative for this p, and then my solution is just e to that antiderivative. I can ignore the constant. It can just set it to be 1. It doesn't matter. So I can just take my function p, find its antiderivative, and then my solution for integrating factor is just e to the antiderivative of p. All right, so let's apply this in a few examples. So our first example is this ODE. So dy dt plus y over t equals t squared. So let's go ahead and use that trick to find our integrating factor. So p of t is just 1 over t. So its antiderivative, a of t, is just log of t. And mu is e to the a of t, which is just e to the log of t, which is t. So now I multiply both sides of my equation by t. T dy dt plus y equals t cubed. Now, this left-hand side here is the derivative in t of ty. All right, we know from our setup it should be a derivative of mu times y, but you can also just calculate that out. If the derivative falls on t, I just get y. If the derivative falls on the y, I get t dy dt equals t cubed. And now I can integrate both sides. So ty equals t to the 4th over 4 plus a constant. And so then y equals t cubed over 4 plus c over t. All right, and that has solved our first order linear equation up to an initial condition. So let's say we have the initial condition y of 2 equals 3. Then I can plug in here and say that I want 3 equals 2 cubed over 4 plus c over 2. 2 cubed is 8, so this is a 2 plus c over 2 equals 3. And solving this out, I see that I want c equals 2. So my solution is y equals t cubed over 4 plus 2 over t. And that solves our initial value problem for a first order linear equation. All right, second example. So here's our second example. dy dt plus cosine of ty equals t. Now, we can use the same trick as before. Our p of t is cosine of t. So its antiderivative is sine of t. And so our integrating factor is e to the sine of t. Yes, it looks nasty, but it does the job. So let's multiply both sides by mu, and I get e to the sine of t dy dt plus e to the sine of t cosine of t y equals t e to the sine of t. Now, as we were talking about before, this left-hand side is... So, as we were talking about before, this left-hand side is the derivative in t of e to the sine of t y equals t e to the sine of t, which is how we defined our mu. And now we can integrate both sides. So e sine of t y equals the integral of s e to the sine of s ds plus a constant. And now that integral can't be explicitly determined. There's no way to actually compute what that integral is in terms of actual functions, so we have to just leave it alone as it is. So dividing through by e to the sine of t, we get that y of t equals 1 over e to the sine of t times integral, and I'm going to put definite bounds in just to show where the t shows up, s e to the sine of s ds plus c. And this would be something you could then solve out numerically or use some sort of solver to sort of graph the curve, but you can't really do much more analytically at this point because there's no way to actually integrate s e to the sine of s. So this one you kind of have to leave as it is, which is kind of unfortunate, but it is what it is for the problem. Leave that one as is, and that would be your answer for this problem. All right, those are the two examples I wanted to go through. I've got one more problem for you to work through on your own for this, so I'm going to put that down here below. I'll put that up for you right now. All right, so there's another problem for you guys to work on. Take a look at that, put that out on the worksheet, and bring that to me in class tomorrow. Thanks a lot for watching, and I will see you in the next video.